Hi everyone. Starting this lecture, we're going to try to prove in earnest the small data global Wellposedness theorems for the semi-linear wave and Klein-Gordon equations that we have been discussing up to now. Now, before we get started, I'm going to apologize for switching the format on you. I realized after a few false starts that it is somewhat difficult to cut this discussion into nice, digestible 10-minute chunks that's independent from each other. And so I'm going to have to violate what I said in the beginning of the semester and actually make longer videos using a different software. And part of the reason is because the proof that we'll be using actually is heavily interconnected using many ideas that we have presented up to now. And using the shorts format that I have been doing before, it's harder to refer back to previously derived results. And so I'm going to use this format here to make it a little easier to follow the discussion. Now, so to make it a little bit easier on you also, I'll have posted the PDFs of the underlying presentation, which I'm going to be scrolling through now and talking about on the course website next to the videos. So I encourage you to download a copy of the PDF if you have a second device that you can scroll along and cross-reference as you need. And maybe you can even make annotations and take notes on it directly. Okay. So with that little bit preamble out of the way, I want to start talking about, like I said, the small data global Wellposedness. Now, let's start by sort of reviewing what are the known facts that we're working with. So first, we're trying to study a semi-linear equation so that we have the left-hand side being box M of the of phi, the solution we're looking for. Okay, the right-hand side in homogeneity is going to be a nonlinear function of phi and its derivatives. Okay, and then we have assumed that the form of linearity is such that for the wave equation, we're going to look at f of the derivative of phi only. And for the Klein-Gordon equations, we're going to look at f of phi and its first derivative. Okay, and we assume that this f function is a smooth function of its argument. And we're going to assume that it vanishes to order 2 at origin, meaning that if you look at the absolute value of f near the origin, it's going to be big O of the quadratic of phi and quadratic of d phi. Okay? So that's the assumption on nonlinearity. And the quadratic vanishing order to a true condition is basically just to guarantee that f really is a nonlinearity, right? That that all the linear terms are accounted for in the left-hand side, right? If there were actually a linear order vanishing of the function f, then tightly expanding f can write it as the linear part plus the quadratic and higher parts, and the linear part would actually comes into the left-hand side, become part of the linear equation. Okay, so that's our form of nonlinearity, and I also want to recall for ourselves that we have the following dispersive estimate. I'm going to state it in a form that's slightly different from what we did before. Before when I proved the dispersive estimates, I was very careful in writing down the precise interpolation, argument, everything like that. But for our purposes, for this small data global Wellposedness result that we've been proving, we can just replace all the lower order Sobolev spaces, so weighted Sobolev spaces on the right hand side, by the highest order one, right? So previously what we did is that we can obtain the L infinity estimate, and with the right hand side being interpolation of a high order derivative one and the low order derivative one, interpolation between two different spaces. Now, obviously, the low order derivative Sobolev space is incorporated as a subspace of it contains the high order one as a subspace, right? So if we so we could actually, or in other words, the norm of the higher order Sobolev space contains the norm of the smaller one as a portion. So we could easily replace all lower order ones with the highest order that appears on the right hand side, and just to simplify the presentation a little bit so I don't have to keep track of all the fractions that comes up everywhere. Okay, so all right, so we have the following dispersive estimate. Oh, and actually, you could actually do the argument that I'm going to present next using these interpolated versions, and that will actually give you some savings in our derivatives you'll be needing. And I will point that out a little bit later when we come to the actual nonlinear argument, how this might work. But for now, just think about the simplest possible case. Okay. All right. What is our strategy? Our strategy to prove the global Wellposedness theorem is that something we discussed in the previous two lectures, that if we're given sort of phi 9 and phi 1, so two initial conditions, and we're going to assume they have compact support, And we mentioned why before, because we want to actually take use of the dispersive properties. And for now, the easiest way to do so is to assume that it has complex support, because we need to assume that it has some sort of concentration of support before we can actually get dispersion. Okay, and right now, if we just sort of don't assume complex support and just use a whole space, then you have to sort of do truncations and things like that, and you have to be careful about how fast you're going to assume the initial data decays towards infinity. So rather than trying to work out all those technical details, we're going to look at the situation where it has complex support with guaranteed decay at infinity, because outside a ball is going to be 0. So we're going to assume that phi0 and phi1 have complex support on the ball radius 1, center of origin, and we're going to try to solve the semi-linear equation on the domain t greater than or equal to 2. Right? This is just to make it a little bit more compatible with the kind of dispersive estimate that we have proven. And so what we're going to do is we're going to prescribe initial data at t equal to 2. And as I said before, this will guarantee that the solution, by the finite spatial propagation property, live within a light cone. It's going to be living within a light cone where t is greater than or equal to x plus 1. Okay? So what we're going to be doing is we're going to use the same idea what we did for proving the existence theorems for the nonlinear Schrodinger equation. Namely, we're going to try to use a contraction mapping argument. Okay? So what we're going to do is we're going to try to find a fixed point of the following mapping, this mapping rho. Now, I'm going to define rho as what? As rho of capital phi. Capital phi here is just the vector of phi in its first time derivative, phi comma dt phi. Okay? This we're going to set it as the linear evolution operator u, right? This is the solution to a linear wave equation or linear Klein-Gordon equation, depending on whether m is positive or 0. Okay? And we're going to look at this applied initial data. Now, I'm evaluating u at t minus 2 because I'm prescribing initial data at t equal to 2. Okay, so at t equal to 2, this is going to be u of 0, right? So I'm going to look at, so for later time, the time that has elapsed from the initial data is t minus 2, and that's why I'm using u of t minus 2 as my evolutionary operator, ut of minus 2, at the initial data. And again, phi0, capital phi0 is going to be the pair, small phi0 and small phi1. This is the initial data pair. Okay, and now I have the inhomogeneity, and this is going to be using when presenting it using Duhamel's principle as an integral from the initial time, which is t equal to 2, to the time I'm trying to solve to, which is small t, of u of t minus s of the inhomogeneity placing the second component of this vector 0 f of s ds. And of course, f here is the nonlinearity that we're going to be looking at. Okay. Now, so what we're going to do is that we're going to look at f being f of the function of the putative solution, capital phi. Right? So meaning that we're going to take this capital phi and plug it into capital F the way that you will plug solution in. So we're looking at the phi in its first derivative, and then we'll plug it in. Okay? And so the idea is that this is just going to give you a mapping from what? From generated from the initial data phi0 and this input capital phi, right? And we're going to generate a new function, a new space-time function defined on t greater than or equal to 2. Okay? So our goal is to argue that, okay, using the Duhamel's principle, a solution to the original nonlinear wave equation, nonlinear Klein-Gordon equation, is going to be arising from a fixed point of this rho mapping. Okay? So now the main issue here is that we want to try to define this rho mapping and get a fixed point. And so in order to do so, we have to talk about in what function space we can try to do this mapping. So we want in particular, we want if capital phi, the input to this rho mapping, belongs to some function space, right? We want its output, rho of phi, to be in the very same function space. And the fact that we have this being in the same function space, right, will be the first step toward being able to prove that it's a contraction mapping. Okay? So in the end of the day, however, this also tells us that this function space will be the function space in which the solution actually lives. Okay, so the key question we want to answer is, what is a function space? How do I make this rho a contraction mapping? Can I choose a function space, or maybe some function space, or a subset on which this rho is a self-map and is a contraction mapping? So that is our strategy. Okay, our strategy is to use the contraction mapping property, contraction mapping principle, to create a fixed point, and the fixed point will become a solution to the nonlinear equation. Okay, and this is sort of, as I said before, this is the general method with which that we attack semi-linear equations. So semi-linear equations are often attacked using a fixed point argument as such. Okay, so how do we actually proceed with this? So our idea. So this is an idea that we managed to talk about a little bit earlier, but let me just sort of reiterate it a little bit, just so that we can really get under the skin of this idea, so we can actually understand what's going on. So the key idea is that we want this formula rho to make sense. So what do I mean by that? So we have this formula here, rho. Okay, so let me just take maybe a color to highlight it. So this formula rho here, we want it to make sense. Okay, now how can it make sense? Well, let's look at the component. We have the evolutionary operator u. Let's plug it into everything, like everywhere. And the key question is, what is the domain of u? The domain of u, right, as we have discussed earlier, the linear solution operator, we have only treated the situation where the linear solution operator has its domain, either the Schwarz functions or the L2 functions, right? So we need to have at least that. So we're going to assume compact support. So okay. So what we're going to care about is that we want to make sure that the thing that we plug into this capital U are going to be L2 functions, because that will allow rho to make sense. Okay. So for the function to make sense, we need the thing plugged into U to be L2, and the initial data part, right? We can always just assume the initial data is in some L2 space or some higher Sobolev space, and it will be automatically being L2. The key difficulty, however, is to guarantee that a nonlinearity when doing this argument is going to be in L2. In particular, so F, so if you're plugging a capital phi into the formula for capital F, right, you're going to spit out a L2 function. Now, capital phi, we should say, okay, capital phi, we're going to construct it from this process, and therefore it's also automatically going to be in L2 in every time slice. However, because f is a nonlinear function, and we know that when you multiply two L2 functions, you're not generically going to get a new L2 functions, right? If you multiply one L2 function by another L2 function using Cauchy-Schwarz, you only get product being in L1 and not in L2. Okay, so since the nonlinear functions are not going to guarantee to be in L2, we have to think carefully about how can we guarantee that for every single time s, if you evaluate f of phi at the time s, this is going to give you an L2 function. Okay, and so that's sort of the motivating idea behind all the construction that we're going to be doing. We want to make sense of, we want to try to have a way of making sense of this this function rho, and also getting control on how big the output of rho is compared to its input. And in order to do so, right, we're going to first answer the question: how can we make a nonlinearity in L2? Now let's go back to our nonlinearity f then. We know that f is quadratic at origin, right? This is our assumption. So this means that we can actually apply the Milgrom's preparation theorem, okay, which essentially says that in the ring of smooth functions, you can do division. Okay, if you sort of with property with zeros at various places. So in other words, if f is quadratic at origin, this tells us that we can take that a smooth function f, which depends on its argument, can be written as what? Since it's quadratic at origin, it tells us that the smooth function can be written as some smooth function g of its arguments multiplied phi and d phi. Basically, you can divide by phi and divide by d phi, and you still make sense. Okay, so I'm not so this, I mean that this is sort of matrix multiplication. So I can say, since with respect to the phi component, you can divide by phi. With respect to the d phi component, you can divide by d phi. You can write it as something times phi and something times d phi and add them together. You can reconstitute f by this process. Okay, and in particular, since f is quadratic, this means that g is going to be linear. So g vanishes to first order at the origin. So g at the origin is 0 and smooth, but the first derivative may be non-zero. Okay, so we have that f can be written in this way. So if we want to guarantee that this output of the function f, right, is in L2, a sufficient condition is that the input to this is not only L2 function, but also in L infinity. Why is that? If we know that phi and d phi are L infinity, right, uniformly bounded, right, then we know that if they're uniformly bounded, that means that because g is linearly, right, it's a linear function, so it vanishes linearly at the origin, right, So for you know that there actually is a, let's say, a increasing function of of the absolute value of phi and d phi, such that g is bounded by this increasing function of its absolute value. Okay. And so if phi and d phi are infinity, that means that g, the factor, will also be uniformly bounded, right? Because g is a smooth function of these things, and smooth function of bounded things is going to be a bounded thing. So you have uniformly bounded g multiplied by L2 function phi and d phi, then this will guarantee that this becomes something that's in L2. So essentially what we're saying is that I can try to put this factor in L infinity and put this factor in L2, and this will guarantee that f is in L2. Okay? So this we have already actually seen one version of this earlier when we talked about local Wellposedness theorem. So in local Wellposedness theorem, what we did is that we used the Sobolev embedding theorem, where we said that if you have an L2 an object in the L2 Sobolev space HD has plus 1, right? This embeds into L infinity. Okay, so because of that, we can actually prove that phi d phi in HD has plus 1 implies that f is in HD has plus 1, and in particular f is in L2. Okay, and this argument that we talked about earlier when we talked about the product properties of the of nonlinearity when we talked about local Wellposedness result. So this has been explained previously, and so I'm not going to dwell on it too much. Now the question is, what do we do for the global Wellposedness result? Okay, and so as I mentioned in the previous two lectures, right, the if we just use the same sort of argument, if we the best we can expect is what is that the L2 norm, because we're solving a wave equation, right? And wave equation is essentially conservative, which tells you that the L2 norm of the solution at a given time step, at best, is going to be a bounded function of time. You cannot expect it to decay, because when you look at energy estimate, there's always going to be the incoming flux from the initial data, and that is a constant. And so there's a lower bound to what you can expect the energy fluxes on later slices. So if we just if we just assume that phi and d phi are in some L2 Sobolev space, right? The best we can do is we can assume that this is uniformly bounded in time. But if you plug this back into this argument, right, this tells us that f in this Sobolev norm is also going to be uniformly bounded in time. That's our best estimate. And when we're integrated from 0 to t, or to 2 to t, right, this is going to grow now linearly in time, and which will immediately violate our initial assumption that my functions are bounded. My functions are such that their Sobolev space norms on constant t slices are bounded uniformly in time. Okay, so we're going to run into a contradiction. This is what we talked about in the previous two lectures, right? So what we're going to do is that instead of trying to use this naive Sobolev space estimate, we're going to try to use dispersive estimates, because dispersive estimates will allow us to pick up a decaying factor of the L infinity norm, right, from a bounded L2 object. Okay, and this is precisely what we had before, right? Our dispersive estimate here, in top here. Here, this object here, on the right-hand side, this is up to some powers of t. So if you take this multiplied by tau to the power d half roughly, this is going to give you something that's controlled by the energy of the solution. Okay. In particular, if we have constant energy, right? If we have sort of bounded energy, this thing multiplied by tau to the d half. Remember, tau is the hyperboloidal parameter. It's going to be bounded. So if this is bounded, right, then the left-hand side, that tau to the d over 2, together with the weight below, this is going to give you a weight on the L infinity norm. And this weight is going to guarantee that my L infinity norm of my function is going to be decaying. And so with this decaying weight, right, then we'll have a hope that we're getting some decay somewhere, and then the L2 norm of f is actually going to be integrable. L2 norm of the capital F is actually going to be integrable. Okay, so this is sort of what we explained a couple lectures ago, right? But now let's just try to sort of see how we can actually make use of dispersive estimate and make this work for the global Wellposedness situation. So let's just start by an example, a very quick example for the Wilson wave equation, okay, because it's a little bit simpler. Okay, so And this is just an example of the kind of arguments we'll be using, but this is not the full proof yet, because we will see while doing this example that there are some complications that are arising if we do things like this. So we're going to suppose that the energy flux on sigma tau, remember sigma tau, these are just hyperboloids, right? These are hyperboloids. Suppose the energy flux through sigma tau are uniformly bounded. So we suppose that we have some phi for which the energy flux through is uniformly bounded, and we're going to assume that this is uniformly bounded for up to some number of L derivatives. So this is up to some number of L derivatives. And remember that we like the L derivatives. Why? Because the L derivatives commute with the wave operator. So in particular, note that if we know that if let's say if like this phi solves the inhomogeneous equation, right? So for now, forget about f being nonlinear. Just think about f as being some arbitrary given initial given nonlinearity. Then I know that box M of L acting on phi is equal to L acting on, oh, this is capital F here. Okay, so we have this, right? So what we are trying to do then is that we want to try to assume that for now that somehow this equation satisfied by box ML mini L setting on phi is also good. Not only that the equation satisfied by box M phi equal to F is good, but the equation satisfied by box M L phi equal to L F is also a good equation, such that the energy flux of phi and its all higher L derivatives are going to be uniformly bounded along sigma tau for all sigma tau. So in other words, if you take this, going back to what the energy controls, right? The energy flux controls. The energy flux controls the following object. The energy flux actually controls tau to the power d multiplied by the time derivative of phi measured in the weighted solar space wk2 minus 1 squared, right? So this is k L derivatives acting on t phi, okay? And this plus, we're going to have tau to the power d minus 2 with, this is L phi, so this is sort of generic L directions, L phi measured in also the same space, wk2 minus 1 squared, okay? And this is the object controlled by the energy flux. So this is that the energy, if the energy flux is uniformly bounded, then this particular quantity as written down on over here is also going to be uniformly bounded. Okay, and we're going to also assume for now that support of phi is within this t bigger than or equal to x plus 1, because this will be what will happen when we try to solve the nonlinear equation by the finite speed propagation property, right? We have the initial data is restricted to ball radius 1 at t equal to 2, and therefore to a future of t equal to 2, the support of the solution by the finite speed propagation property is going to be within this region. T is bigger than or equal to x plus 1. This will be a line cone centered at t equal to 1, x equal to 0. Okay, so we're going to assume these things. Then if we use a dispersive estimate, right, and this is something that we talked about earlier, right? We already shown the version that we'll be using earlier, and if we just sort of plug everything in and chug a little bit, we see that for the wave equation, this guarantees that the phi's first derivative is going to be bounded by some constant multiplied by m being the uniform upper bound to the, also it should be square root of m actually. It should be a square root of m. So this will be the constant upper bound of to the energy flux, okay, divided by t to the d minus 1 over 2. Okay, this is the decay rate that we have for the wave equation. We talked about this earlier. We talked about the decay rate for the homogeneous linear wave equation. Okay, so let's look at f of the derivative of phi, right? Between the wave equation case. So we're caring about the nonlinearity being f acting on the derivative. And so this is going to be also talked about before by Milgram's propagation theorem. This is equal to g of the derivative multiplied by some derivative. And this function is in L2. Okay, this function is in L2. And why? This is because I know that d phi is going to be in is going to be L infinity, right? Because we've already established that with phi, we assume that phi has uniformly bounded energy flux. This guarantees that d phi is L infinity and has the following decay bound. So we can plug it into G and get not only that G uniformly bounded, but because G we know is decaying linearly to 0, and I will know that as t goes to infinity, square root of m over t over t to the power d minus 1 over 2 is going towards 0, right? This tells you that that we actually have, given this m, we can write that G of d phi is going to be bounded by some constant multiplied by m over t to the power d minus 1 over 2. This is entirely using the fact that G is linearly 0, and I justify that in the parentheses below. Okay. So once we have this, then it tells you that F, the nonlinearity now, right, it's going to be bounded by a decaying factor, we call uniform energy bound. So this again square root of m over here, uniform energy bound divided by t to the power d minus 1 over 2. This is decaying in time, multiplied by d phi in L2. Multiplied by d phi in L2. All right. And so this will actually tells us that F measured in L2 is going to be something that is this factor, which we expect, and most we can expect is bounded uniformly in time. Okay. But this is multiplying by something that is decaying time. Remember, t is bigger than or equal to 2. And so we have some hope now, right? We have a uniform bounded quantity multiplied by something as 1 over t to some power, and this we have a chance of actually integrating in time and guaranteeing that sort of when we look at the Duhamel principle, right? When we integrate this f of d phi in L2 in time, we integrate this in time to feed back into the Duhamel principle. This would help us guarantee that my energy remain uniformly bounded, right? Because previously, remember, the issue is that if we only assume the Sobolev, the usual Sobolev norms of the solution remain bounded in time, right? Then when we take the naive argument where we estimate L infinity by the Sobolev norm, right? This only guarantees that the L infinity norm is bounded uniformly in time, and therefore when you integrate the Duhamel's principle in time to get a solution, this will tell us the solution has to be measured in L2 in Sobolev space, has to be growing linearly in time. Here, however, what we did is that we're using the fact that if we assume bounded energy flux through the hyperboloids, then and this is measured relative to the L derivatives, right? Then this guarantees that my L infinity norm is actually decaying in time, and so the corresponding energy fluxes, when you do energy estimate, which will be depending again on the time integral of the L2 of the integrals of F, this is going to become time integrals of something weighted by a decaying factors of time, and therefore it could become actually integrable. All right, so that is sort of the basic idea. So now let's return to our strategy again. Okay, so step one, in order to make sense of this rho, right, this mapping from a putative solution to a new solution, right, we need the energy flux for some higher order L derivatives of the phi to be bounded. Okay, so this is basically what I just did in the previous step. And then to use the contraction mapping argument, right, what do we need? We need that the boundedness of the energy flux for the input implies the boundedness of the energy flux for the output, right? This is the first step. Well, I need to have a way to measure the input and output to be the same, so that we can actually think of this as a mapping within certain function spaces. And secondly, we also need that to prove that rho is a contraction. Okay, so all right, so basically, just to summarize what we have so far, we have concluded that if we can assume that a sufficiently large number L derivative of phi can have bounded energy flux, through hyperboloids, then we can actually make sense of the operator rho, because we can guarantee that the nonlinearity is going to be for every single fixed time in L2, and this will guarantee that this rho operator actually makes sense. And once it makes sense, then we can start trying to prove that it has better regularity, better bonds. But the first step is to make sure that it makes sense, right? And so rho can be made sense if we assume that we have enough L derivatives and such that their energy fluxes are bounded. And then after making sense of rho, now we have to actually try to make sure that rho can be extended. So rho, as stood, right, is a mapping from some capital phi such that you have certain bounded energy flux property, and you want to make sure that the output is going to be of the same type, right? And then it's contraction mapping for us to actually use the contraction mapping argument. And so the second step will be to prove these higher order L energy control on the generated solution, a rho of phi, okay, and see what we can say about that. Okay, all right, I think this is sort of enough for a first half lecture. Let's take a break and we'll continue with the second part of the discussion.